my pleasure to share with you seismic and wind design considerations for wood frame structures. Before we get started, I would like to begin with a brief introduction of APA and the services we provide for those of you who may not be familiar. You may have think of APA as the American Plywood Association, yet today we are actually APA, the Engineered Wood Association, and that our members are manufacturers not just in the United States, but also in Canada, producing in addition to plywood, oriented strand board, OSB, glue laminated beams, gluLams, I-joists, structural composite lumber, SCL, which is comprised of laminated veneer lumber, LVL, LSL, PSL, and OSL. These glued wood products are commonly specified and constructed in wood frame structures today, and as a trade association, we provide three main services, or through our three divisions, as shown on this slide here. Beginning with our Quality Services Division, this is likely the most important service, as the building code requires that these materials are tested by a third party, and the process is provided through our auditors and our regional labs that visit the mills to make sure that the materials are meeting the manufacturing standard. And in the end, a grade mark is stamped on the material. So we will look at a couple of grade marks today, as this is very helpful to you when you are providing your specification or when you're out at the job site verifying that the panels that you specified are in fact what were installed to meet your shear wall and diaphragm needs. Secondly, we have our Technical Services Division located in Tacoma, Washington. Here we have a research facility with engineers and wood scientists producing research and looking at new ways to implement these products in construction today. And one of these research projects is our recent force transfer around opening shear wall research that we will touch on at the end of our program as well, as many of the code developments that go into Chapter 23 of the Building Code, the various chapters of the Residential Code, as well as the special design provisions for wind and seismic in the National Design Specification for Wood Construction, which are, again, referenced from Chapter 23 of the Building Code. And finally, we have our field services. As Ali mentioned, I'm a local field representative for the West Coast. I'm located in San Diego, California, and my territory is California, Arizona, and Nevada. We have colleagues spread throughout the United States and one in Canada, and our job is to be a technical resource to the industry. So we work with architects, engineers, building officials, and builders. Knowing that we're available, please do not hesitate to contact me or my colleague that is closest to you and where you're working next week, next month, next year, when you have any questions about how these products are implemented in construction today. A few APA recognitions to quickly share with you. As you can see from this long list, we have a lot of experience in the codes and standards developments for wood frame construction. Two items I did want to share of note today was first the 6 approved ANSI standards that APA is involved with. Engineered wood siding, cross-laminated timber, CLT, that's a new material in construction today that I'll be touching on more next week for the webinar if you'll be attending. The engineered wood rim boards, and then the glulam standards, which you likely are familiar with AITC. You may not be aware that AITC has closed their doors, so APA has now taken over these ANSI standards, and they are available on our website. If your specifications still refer to AITC, you'll want to update that simply to replace it with ANSI in front. And the other item of note is that on our website you can find product reports. Many of our manufacturers will have a dual APA product report as well as an ICCES report. Something new, however, is that we are available to produce joint product reports with ICCES, which would be an ICCES APA evaluation report, have both of the organizations shown on the product report for your use. Today's agenda will begin with load path continuity, look at the building code updates, and then finish with our shear wall design alternatives, including the shear wall research that I mentioned a moment ago. Building code says that we need to make sure we provide a complete load path using rational analysis that's capable of transferring the loads from their point of origin to the load-resisting elements. And this needs to be done in both the vertical load path as well as our horizontal load path. And the horizontal load path, as we can see just by this quick simple diagrams left and right, is that the horizontal load path is more circuitous in nature. It's not as direct as our vertical load path, and therefore there's opportunities for a lateral load path failure to occur more readily than a vertical load path. So a little humor to begin our webinar here today. You'll notice that we have an incomplete load path shown in our vertical direction, clear to see, whereas our lateral load path takes more study and experience. So you need to begin by looking at where are you constructing and designing this structure. And here we have the FEMA hazard maps to shed some light on the lateral loads that are going to be most important in your design process. On our left-hand side, we have our wind hazard map, and unlikely a surprise to anyone, we see again this red zone through the middle of the country, aka Tornado Alley, as well as our shaded zone on the southeastern portion of the United States, where hurricanes are more prone. On the right, we have our earthquake hazard map, and again, a red zone on our west coast representing very high seismic loads. And you may, if you're a west coast person, may not be aware that there are other seismic regions to be concerned with, such as the New Madrid Fault in southern Illinois, as well as in the southeast. Useful to consider these loads in the most basic form to understand the impacts of why the code says what it does and influences our design choices, particularly when you look at conventional construction requirements. Many of the conventional ideas take this into account. So first, when we look at our wind force, that force is equal to the wind pressure times the surface area. So as your structure becomes taller and larger, individual segments of the walls go from 8 to 10 feet in height, you of course will have a greater force that you're going to have to design to resist. And our wind loads are designed in accordance with ASCE 710, referenced from Chapter 16 of the Building Code. For our lateral loads regarding seismic or earthquake, that force is equal to the ground acceleration due to the earthquake times the building mass. So again, your choice in building materials are going to impact the force you have to resist. The more mass of your structure, the larger the force. And so when we are considering wood frame construction, this is important to remember. A benefit of wood frame construction is that it does have a high strength to weight ratio, so that's very useful in being able to efficiently design these buildings to resist the force. Yet in California in particular, we have a trend for using a lot of concrete tile on our roof, which will again increase the mass of the building materials and impact our design. And if we were using brick veneer as an alternative as well to stucco, that would increase the mass of our wall section. So again, thinking about these very basic formulas will help us when we're thinking about our design effects. And so the next item I'd like to share with you is some photos that we've collected over the years that demonstrate our general modes of failure: uplift, base shear, racking, and overturning. One of the items that APA provides or services when there is an event, a wind event or earthquake, we send out our local field rep when feasible to take photos, write a report. We have several publications on our website that have come out of these research or investigations following tornadoes, Hurricane Katrina, for example, that you can refer back to in the future. And in my experience, when I started with APA, I actually began working in Chicago. A lot of opportunity, of course, to look at wind events, and did go to view damage after 2 tornadoes in Springfield, Illinois, as well as southern Wisconsin, and it really reinforced what I had always known via the building code and what I had implemented in my designs in the past as well. So we begin with uplift here, and you can see that very typical home with a great room, a 2-story opening in that location. There was a pressurization of into the inside of this room, and a failure at our connection of our rafter to our top plate. So if you could zoom into this connection, what do you think would be tying our rafter to our plates? Likely toenails. And so here we see our toenail, and although the wood structural panel, in this case OSB, did remain connected to the rafter, we need to make sure that we have that continuous load path from point of origin all the way down to our foundation. So the failure in this particular case was the connection of the rafter to the plates. What would be a better way to connect this material? 3D connector. So there are many shapes and sizes of 3D connectors available by several manufacturers, and APA is not partial to one in particular. However, what we see here is that we are going to be loading this connection in a more pure manner than a toenail, where the toenail is going to be at an angle, and the NDS it specifies the specific angle that it should be installed at and the dimension within the members. And of course, there is a reduction for using toenails, acknowledging the fact that it's not going to be a perfect installation. So we consider these 3D connectors cheap insurance, whether you have a lateral load coming through this connection, or you have uplift on the connection, or even out of plane of the wind or the earthquake loading this connection. It's going to be a better way to resist. Similar concept is shown here by taking the wood structural panel and lapping it from floor to floor. Rather than relying on the wood structural panel as just providing your shear or your racking resistance, in this instance you're lapping it from floor to floor, which is going to allow it to provide combined shear and uplift. And we do have some design guides on our website to assist you in providing this design. And many of the wood structural panels are produced in longer lengths as well. So depending on the height of the wall that you're designing, if it's an 8 or 9 foot tall wall, 10 foot tall panels are commonly provided in the marketplace today, 4 feet wide by 8 to 10 feet in length. Base shear is another failure mechanism that we need to design to prevent, and here we see an extreme failure at the base. Although again, you see a case where, for the most part the building performed quite well. We need to make sure we get that all the way down into our foundation. And if you take your structural engineering hat off for a moment and you put your mechanical engineering hat on, we can think about the other impacts to this failure. In addition to the structure itself, we're looking at severing our utilities, our gas, our water lines. And then racking resistance. This photo is taken from the LA Basin area. It was under construction. An earthquake occurred, and we see that we did not have the ability to resist that racking force on the building. So our shear walls are there to provide that racking resistance and keep our building upright and vertical. So the studs are shown here are going to be transferring that gravity load, whereas our shear walls as demonstrated in the right-hand side of the photo, is going to provide that racking resistance. And so the building code goes into great detail regarding height-to-width ratios and other items of the like to properly design those to be able to transfer those loads, which is another great topic to keep in mind as we visualize this slide next. Here we have a small garage, and here you can visualize the wind load. This was from a tornado on the right-hand side of the garage, and a portion of that load goes directly into the foundation. The rest of it goes up into our diaphragm. And in a wood structure, your diaphragm is composed of the wood structural panels attached to the trusses, rafters, or floor joists, depending on what level you're at. That load is then resisted by the walls in the opposite direction. So in the back of the garage, if you look closely, you see a window opening, but for the most part, a very solid wall. In the front, of course, we have very skinny walls. So our design options here, perhaps a open front structure was designed, more likely with the size of the building. There was not such a comprehensive design, and there should have been larger shear walls or wall bracing segments to resist this force. We don't have overturning of entire structures. This is a picture of a soft story failure. But rather with overturning, we think of resisting the overturning on individual shear wall segments. And this is done through the use of hold downs. So putting it all back together in a very simple box, we would load our lateral load in one direction. Here we're showing a wind loading. And again, that wind is going to be transferred into our diaphragm. The diaphragm is going to distribute the loads via their chord forces, the drags, into our shear walls in the opposite direction. And the shear walls need to resist the racking, overturning, and the sliding at the base of the shear wall. Which will bring us now to our building code updates. The 2012 International Building Code is being adopted in many areas today, and with regard to wood frame construction, we want to be mindful of Chapter 16 for your loads, and again, ASCE 7 is the reference standard. In Chapter 23, for the wood chapter, you may have noticed that Chapter 23 is appearing to become sparser and sparser with each code cycle, and that's because, like steel and concrete chapters, the wood chapter now is referencing you outside to the standard, and the standard for the wood frame construction is the National Design Specification for Wood Construction, the NDS, that is published by AWC, the American Wood Council. And the current version is our NDS 2012. Another document that is part of the NDS package is the SDPWS Special Design Provisions for Wind and Seismic, and that's the 2008 version currently. The SDPWS should actually be pronounced according to the acronym SDPWS, but you'll hear people call it SDPWS just for ease of pronunciation. And this document has the lateral information provided within it, and it is a free download currently. So if you have not downloaded it yet, please take a few minutes to do so. It's available at this link at the American Wood Council website, and will be your resource for what you're used to seeing within the Chapter 23 directly. Some things to be aware of, we're going to look at, though, how those tables have changed. They're now nominal values, and some other items that have been updated within the new 2012 IBC. The good news is the changes are not overly grand, and so that should make your update process easier to maintain. So we'll go ahead and go through this list quickly. First, this is not a change yet. I get this question again and again. So I need to begin by saying that wood structural panels are by definition either plywood or oriented strand board OSB as defined in both the building code 2302 as well as the residential code R202. And often we'll speak of plywood generically. So you might want to take a moment and review your specifications to see if you have plywood referenced in your structural notes or in your specifications, or even further, you may have CDX. And CDX means specifically plywood with a C face, a D back, and exterior rated glue. Well, many of the plywood panels produced today for shear walls and diaphragms are going to be a DD panel that still have the shear resistance that you need. So in the interest of keeping the construction as cost-effective as possible, we recommend, rather than specifying plywood or OSB, to simply specify rated sheathing of the thickness that you need, or struck 1 if you need that additional shear capacity. And struck 1 is also available in both plywood or OSB. The shear capacity of the wood structural panel is a function of the fastener size, spacing, and the panel thickness. So again, bringing us back to the recommendation of focusing on the thickness of the panel as well as the size and spacing of the fasteners is going to provide you with the capacity that you're looking for. And these values are in the tables within the SDPWS-08. You can always calculate them using principles of mechanics. We do have our panel design specification available on our website that lists all of the values for the individual thicknesses of panels, plywood versus OSB, of different plies and layer combinations. But again, our recommendation is to keep it simple when you can and to use the SPIDWIZ and use the generic specification. Likely when you're looking at really sharpening your pencil, it might be a retrofit or an existing project that you're trying to identify whether it's sufficient for the changes that will be occurring. Here's a simple diagram and a grade mark, as I mentioned before. And so this figure that you see on the right-hand side showing your roof covering and your panels on your supporting trusses, our roof diaphragm in this case, is provided within our Engineered Wood Construction Guide, our E30. This is one publication that you likely have within your library of APA publications. You might want to take a moment and see if it's the newest version. All of our publications are available for free download on our website, with the exception of our joint publication with regard to wall bracing that was produced with ICC, and I'll show you a link for that later. Otherwise, you can download these for free. The E30 is useful because it touches on all of the products, provides the shear wall and diaphragm tables in that document as well, and it has these figures, which again is useful for your design process, your detailing, as well as when you go out to the job site. In conjunction with these figures, they're utilized also in our builder's tips. And our builder's tips are typically 1 to 2 page forms that cover common mistakes like buckled roof sheathing, for example. So this figure is shown as well as a list of items for properly constructing it in the field to prevent having any of the common framing mistakes. So keep that in mind. They are available for your mobile builder's tips, since many of us carry a smartphone, as well as the contractors and inspectors as well. On the left-hand side, I did want to draw your attention to the grade mark quickly, again, to assist you when you're doing your specification as well as your verification that what was installed met your spec. So underneath the APA trademark, you have the grade of the panel, and in this case it's rated sheathing. It could say rated sturdy floor, for example. That would be used for our floor sheathing with a tongue and groove edge. It might say rated siding. So again, this line is a placeholder to identify what the panel was optimized for. Rated sheathing is sufficient for your roofs, floors, and your wall sheathing. And we'll see again, the sturdy floor is commonly used for your floor application. The next item here is the span rating. This is for your gravity loading, so for your vertical load path. 32 is the allowable spacing of your roof supports, 16 is for your floor supports. Size for spacing is important to allow the panels to acclimate. Exposure 1 for the durability. Again, because these products are going to be covered with tile, a wall covering, whether that is vinyl siding or stucco, for example, and again the floors with your carpet or tile, the exposure 1 is sufficient. Exterior would only be necessary if it was used for permanent exposure to the elements. For our shear wall and diaphragm in particular, you want to look at the thickness designation, and this has changed. You'll note that we have a decimal thickness shown here, as well as what we're used to seeing, our fractional thickness, 15/32 category. This is what you're going to continue to use to specify the panels as shown in the SPDWS. And this item here is specifically or basically just for the tolerances in the manufacturing process. So if there's any confusion, again, you want to use the fractional thickness for your design as well as for inspection purposes to share with the building department if the question comes up. The standards are printed here to show how the panel was manufactured as well as the member mill. So here you can identify that number, go onto our website, type it in, and find the contact information. For the tables, as I mentioned, they have been removed from Chapter 23. There's still the shear wall and diaphragm tables for staples provided within 23 directly, but all of the nailing tables have been removed to the SPDWS, and it lists it in nominal values, which allows you to use allowable stress design or LRFD, depending on which you prefer. It also incorporates G sub A, which is a new way to calculate your deflection, which we will look at in a moment as well. For our wood diaphragm design, here is our example table taken out of the SPDWS, and you'll see that we have a couple of changes. First, the values are nominal, which at first glance you might think, wow, we have a lot more capacity, but again, that's because you have to adjust it. And secondly, Seismic has been separated from wind. In the past, there was only a single table with a footnote that allowed you to take an increase for a wind-based design. Now they've eliminated that need for the calculation, or perhaps overlooking that footnote by separating it directly for you. When taking the nominal value out of the table, here the SPDWS defines the adjustment that needs to be made. So for allowable stress design, you're going to take a reduction factor of 2.0, and for LRFD, you're going to be multiplying by 0.80. So without further ado, we will begin the discussion of flexible, rigid, and semi-rigid diaphragms. And so this is a question that has to be resolved with all wood frame structures is, do I have a flexible, rigid, or semi-rigid diaphragm? And that greatly affects the shear distribution to your shear walls. And they're very simply put, a flexible analysis, the diaphragm load is distributed based on tributary areas, whereas your rigid is going to distribute the loads to the shear walls based on the wall stiffness and any torsion that's existing on the structure. And a semi-rigid analysis may look like many different things. basically a merging of the two between flexible and rigid, perhaps an envelope solution. Some simple illustrations to show the difference in how a flexible versus rigid analysis can impact the design. Here we see our simple building with a uniform load in the one direction, 3 equal walls evenly spaced. And so with a flexible analysis, you simply distribute the force based on your tributary area. So a quarter of this uniform load goes into each exterior wall, and then half of that load goes into the interior wall line. For a rigid analysis, in this case, we're not accounting for any torsion, and we're assuming that the stiffnesses are the same for each of these walls. You would have an equal distribution of the loads to each of our wall lines. If we change our example slightly to now look at an interior wall line that's half the length, so perhaps half the stiffness, and again the same load, same geometry, spacing of the walls, for our flexible analysis, nothing changes. So again, you're going to have the same 25% into each exterior wall with 50% into your interior wall line. Whereas with your rigid analysis, now only 20% goes into the interior wall as opposed to 40% into the exterior walls. So part of the issue is that the tributary analysis may be easier to do, the flexible using tributary distribution. However, when you get the load into the shear wall line, now if you have wall lines that are twice the length as that interior wall, the rigid analysis would actually be an easier, likely an easier shear wall design to accomplish. So the codes have some guidance as far as how you can identify whether you are going to prescriptively have a flexible diaphragm, calculate it as flexible, prescriptively be rigid, or else be somewhere in between the semi-rigid category. Beginning with the prescriptive flexible diaphragm, please note that this code reference, you want to X that out on your notes. That has been removed at the time this was the CBC 2010 or the IBC 2009, section 1613.6.1, that is now found within ASCE 710 12.3.1.1. And prescriptively, the diaphragm can be considered flexible provided all the following conditions are met. That you have concrete topping that's non-structural and is less than 1.5 inches thick. That each line of your vertical elements of the lateral force resisting system complies with the allowable story drift of ASCE 7 table 12.12-1. That those vertical elements are light framed wall sheet with wood structural panels or steel sheets, and that the cantilever portions of the diaphragm would be designed in accordance with this other section of SPDWS, which is actually a rigid diaphragm analysis for that portion of the diaphragm. The ASCE 7 also has an additional item that allows you to prescriptively consider all single-family structures as being flexible as well. You can calculate the diaphragm as being flexible if you can show that the diaphragm deflection is more than 2 times the average story drift of your adjoining shear walls. That is more likely to occur the longer the diaphragm, as shown in this picture. There are some prescriptive requirements for a rigid analysis for an open front structure or a cantilevered portion of the diaphragm, and these pictures that were in the building code are now contained within the special design provisions for wind and seismic. As shown here, your open front structure, your cantilevered building, and these are very simple diagrams, and we know that they're being used to much larger buildings and wood diaphragms today. If you can't idealize it as flexible or rigid, then again your structural analysis should consider the relative stiffness of the diaphragms and the shear walls, and your deflections should be calculated to identify. And then furthermore, you're going to be starting with some assumptions of what your distribution would be, so that you're picking materials for those shear walls in advance to be able to help you calculate the deflection. And so it is a very iterative process. The semi-rigid, again, can be done in different means and methods. The SDPWS at this time states that diaphragms shall be defined as rigid or flexible. The envelope approach ultimately is commonly used, and when I was doing structural design myself for a structural consulting firm in San Diego, prior to working for the city of San Diego, I commonly use the envelope method, where you end up taking the worst loading to each shear wall line for either the rigid analysis or rigid assumption or a flexible assumption. So we've talked about deflections quite a bit, and in addition to this topic of rigid versus flexible diaphragms, it's also going to assist in meeting our drift limitations and our building separations. The equations of the past were four-term equations, as shown here, where you have your deflections calculated for the shear wall based on the bending, the shear, the nail slip, and the cord splice, or hold down rather, versus for the diaphragm, that's your bending, shear, nail slip, and the cord splice. These equations are available in our document APA L350, and it gives you all of the variables and assists you in providing that calculation as well as examples. That being said, the SDPWS now has three-term equations where they've combined two of the terms from the four-term equations and now incorporated G sub A, and this allows us to account for blocked versus unblocked diaphragms or shear walls. Prior to this, although there is the ability to do an unblocked shear wall, as we will look at, commonly you're going to have blocked shear walls where you may have a difference would be in your diaphragm. If you do not need blocking, that would be one thing that is sometimes taken out of the equation if it's not needed for shear, and again keeping the cost of construction down. Well, four-term equation, we didn't really have a precise way to then account for the deflection, and based on testing that APA had provided, we recommended that you would enhance or increase your deflection times 2.5 if it was unblocked as opposed to a blocked diaphragm. So this is certainly a benefit of having our three-term equation now, so that you can put in the correct G sub A if it's blocked versus unblocked. What is the future of this discussion with flexible, rigid, and semi-rigid? Perhaps what I've covered for you isn't really satisfy what you would like to see, and so there is ongoing research and testing. The American Wood Council has a task group that's working with the Structural Engineers Association of California's Light Frame Committee to improve the language of the SDPWS, looking at those prescriptively rigid diagrams, as we talked about a moment ago, that they were in the codes for a really long time, yet that is being applied to much larger structures. So to bring it up to date with modern construction and eliminating some of the redundancy in the code language, as we've already begun to see where items are being taken out of the building code if it's already covered in ASCE 7 or in SDPWS, to make sure that they are in agreement with one another and not contradicting each other. High-load diaphragms have been in the codes for years as well. If you aren't familiar with them, I wanted to briefly review for you what they look like and what their shear benefits are for diaphragm analysis. And here we see a common use for high-load diaphragms when we have very large roof structures, often in manufacturing facilities or warehouses where they'll have perhaps concrete tilt-up walls and a very large wood roof diaphragm, a panelized roof. And this panelized roof, as you can see in the photo here, is quickly built on the ground in segments. So they go with large sections here. You see your wood structural panel supported by sub-purlins and purlins, then the girders, glulam, or again it might be a hybrid roof where it's a combination of wood and steel supporting the wood structural panels. And this panelized roof, as you might also imagine when we see the size of these structures, this particular roof was over 1 million square feet, constructed in Ontario, California, going to have some very large shear forces to distribute into your diaphragm. And so the high-load diaphragm table is provided in the SPDWS, and you'll use multiple rows of nails. This allows you to go up to an 1,800 pound per lineal foot capacity for allowable stress design and seismic control designs, as opposed to 2520 for a wind control design. Given the nature of the rigorous detailing of these roofs, it does require special inspection as well per section 1704.6.1. And the limiting factor was actually the splitting of the lumber framing. So you will see larger framing supporting these multiple rows of nailing, and that high loading or nailing is not going to be consistent throughout the roof typically. It's going to taper off so that you can be efficient in your design as well. A picture tells 1,000 words, so the figures that are provided in the SPDWS go a long way to helping with your detailing as well as for the construction and the inspection purposes. And what you'll notice again is that you have multiple rows of nails. You do want to make sure that you are spacing them apart as well as staggering them from one another, providing the space between the panels as well. Moving to our shear wall design concepts, and revisiting one of our very first slides, we want to make sure we have our continuous load path from top to bottom. So we want to make sure that our diaphragm is able to first transfer that load into our shear walls. Often wood structural panels are used here to again enhance that load transfer. They can do so with the truss or with the mechanical connections as well. And then if you look very closely at the bottom of this wall, you may see this hold down. And the question is what is it holding down? There should be, of course, the hold down at the edge of the shear wall itself. Another diagram that is shown in our engineered wood construction guide, shown on our right-hand side for wall sheathing installation. And there are builder's tips as well that go into account for making sure that this is done correctly in the field. You want to make sure you have spacing around your edges, 1/8 of an inch space, and that's simply for installation so that the panels can acclimate and stay flat against the walls. If you do have buckling occurring to your wall sheathing, it's very important to note that that does not compromise the shear capacity or the connection structurally. It's going to be an aesthetic issue, which certainly is going to have to be addressed, and you want to minimize that from occurring whenever possible. Another item that you may notice looking from side to side is that the panels are oriented vertically on the right-hand side, and oriented horizontally on the left-hand side. And so many of APA recommendations are going to take into account ease of construction, in addition to making sure, of course, that it's structurally sufficient. And so if you've heard an APA presentation by me in the past, and I've talked about panels, you've probably heard me say long equals strong. And that's true for your vertical loading or your bending of the panels. So here, when we see the long direction of the panels across the supporting members, the studs, that is going to be stronger for the out-of-plane loading on this wall sheathing segment. However, what is the most important thing that we are using our sheathing for? Wall sheathing. That would be our shear capacity. And again, you may recall that the shear capacity is based on the thickness of the panel and the grade, whether it's rated sheathing or struck one, as well as the size and the spacing of the supporting fasteners. And so with that in mind, it doesn't matter if the panels are installed vertically or horizontally. If they're installed horizontally, that will require blocking to be provided behind that horizontal edge, unless, again, they actually design it as an unblocked shear wall, which will take a reduction on the shear capacity beyond what we typically do just with our adjustments as we looked at before. So a commonly 8 to 10 foot tall wall, panels that are commonly 8 to 10 feet in height, their length, it's typically more efficient for the builder to install the panels vertically as opposed to horizontally. So you will see this being done on the right-hand side, and again, that's fine for your shear resistance. On the left-hand side again is a typical grade mark, and you'll see here the same information, and this 3216, again, that's roof and floor span rating. It doesn't have the wall span rating shown here. And for our shear walls, we're really looking at the shear capacity, which is based on the thickness of the panel, 15/32 category, and then the rating, which in this case is just rated sheathing. If it was struck one, it would say that as well. There are some wall sheathing panels available in the market where they have taken into account that they would like to provide a vertical installation as well as having the strength across the supports. And so they manufacture this specifically with the strength direction and the short direction of the panel, and they will be labeled to show you that the strength is going in the short direction, and it'll often say wall and the span rating on that grade mark as well. Aspect ratios are covered again in the SPIDWIS to define what your maximum height-to-width ratio can be to distribute those forces through the shear wall. And that varies depending on what material you're using with structural panels versus gypsum, for example. And for a wind-controlled design, 2-to-1 aspect ratio is sufficient. So for an 8-foot tall wall, that would require a 4-foot long panel. Excuse me, I should say for wind-controlled design, 3.5-to-1 is sufficient. For a seismic control design, you would be limited to 2-to-1, where you have an 8-foot tall wall, which requires 4 feet in length. Now, there is a footnote that says you can use 3.5-to-1. You just simply have to apply a penalty, which is 2 times the actual width over the height for an earthquake-controlled design. So seismic is more stringent in the length required for your height-to-width ratio as opposed to a wind-controlled design. So you can go to that narrower segment, but then apply a penalty. Depending on which shear wall analysis method you're using, that's going to slightly change how that height-to-width ratio is looked at as well. So this figure from the SDPWS-08 Figure 4D and E is applicable to shear walls that are designed in accordance with segmented or perforated shear wall. And you'll notice that the height of the wall is considered from the plate to plate, full height segment. On the other hand, if you're using force transfer around opening, FTAO for short, then that allows you to consider the height of the wall equal to the opening that it's adjacent to. So this gives you a lot more flexibility to be able to use narrower segments and still meet the height to width ratio without taking a reduction. So again, if we use the example of a seismic controlled design, if they were doing a segmented design for an 8-foot tall wall, they would need to have a 4-foot long panel or take that reduction for the 3.5 to 1 ratio. On the other hand, if they designed it adjacent to a 4-foot tall window, now they could go down to 2 feet and still meet the height to width ratio without applying a penalty. So that's one of the main advantages that I have found driving engineers into using force transfer around openings. And we'll look into that further when we get into our shear wall design options. Comparing the differences between wind and seismic, we've been touching on them already. Their table has already separated wind and seismic in the new SPDWS directly. If you have double-sided shear walls, whether that's wind or seismic, you would take twice the strength if they were the same sheathing and nailing on both sides, or you would take 2 times the lesser if it was different from inside to out. For wind design, if you have wood structural panel on the outside and a gypsum panel on the inside, you can add the gypsum shear wall strength to your wood shear wall strength. You cannot do that for a seismic control design. So that's one advantage for wind control design. Other advantages are, again, a 40% increase in capacity for wind versus seismic. That was covered in a footnote to the table. Now it's directly separated. And then the 3.5 to 1 maximum aspect ratio without penalty. As I mentioned, there is the ability to use that same aspect ratio for seismic design, but then your penalty that you would apply to your capacity would be equivalent to multiplying it times 2 times the actual width over the height. So if we compare a wall that would be designed in accordance with wind versus seismic to really just demonstrate the differences, we have a 7/16 category OSB panel, 8-penny common nails at 3 inches on center at the edge, 6 in the field, gypsum on the opposite face. It's 2 feet 4 inches wide by 8 feet tall. So it violates the 2 to 1 aspect ratio. So looking at what we would have for wind capacity, this is unnecessary now. As I said, that was in the past when you had to apply the adjustment for wind yourself. That's already done for you in the nominal value table. And then you'd multiply it times the length without any penalty. You could also add in the strength of that gypsum on the opposite face. For seismic, on the contrary, you have that same value that you begin with, and now take the reduction for 2 times the actual width over the height times the length of the wall, and you have almost a third of the capacity for a seismic control design as opposed to a wind control design. A note on that, you might wonder why wind gets the benefit of a larger value, a 40% increase, and my understanding that that is based on our knowledge of wind events as opposed to earthquake. We have a greater comfort level with how our buildings perform due to wind as opposed to earthquakes, and so that gives the ability to take that increase. Unblocked shear walls, as I mentioned earlier, is an option in the code today. The SPDWS has a table for the adjustment factor you have to apply if you do have an unblocked shear wall. And so depending on your nailing at the edges as well as the field nailing for your intermediate studs, and then the spacing of the studs themselves, that's going to affect your adjustment. So typically we're looking at 6 and 12, and that might be even tighter nailing, of course, where we have our higher seismic loads. But at a minimum, APA recommends 6 and 12 for your nailing. And we often have 16-inch on center stud spacing. You would have to apply a 0.6 adjustment if the horizontal edges were not blocked. With advanced framing, it's becoming a new concept that's being used more frequently. We might be moving from 16 to 24-inch on center stud spacing. And again, you see a greater reduction that would be applied as a result. And therefore, I don't see this being used much in new design. However, if you have an existing structure that you're looking at what the capacity of the shear wall is and it did not have the blocking provided and you cannot provide it in part of the retrofit, this might be a good solution or option to consider. So moving into our design methods for shear wall analysis, the code and now the SPDWS gives you 3 options: segmented shear walls and then shear walls with openings, which could be done using either the empirically based perforated shear wall method or force transfer around openings, FTAO. And what that might look like is shown in these 3 snapshots. And the good thing to note is that you can mix and match. There's no requirement that says you have to use one method for the entire building. And generally speaking, you're going to create the best design in the end if you use a combination. Often we start with segmented as it's the original design method for our shear walls, where we're looking at just the full height segments, and we're not going to account for any sheathing above or below our openings. If you look very closely, you can see some open studs, and then you even see open studs here adjacent. So they're only sheathing where they had their shear walls that met the height to width ratio. You still have your traditional 3.5 to 1 or 2 to 1 aspect ratio that needs to be met, depending on if it's an earthquake or wind control design. The next option shown here is force transfer around openings, which is, as the name implies, you're going to transfer the force around the opening, typically using metal strapping on the exterior for the tension forces. Compression forces are distributed from the blocking on the inside of the wall, and then the shear force again through our shear panels that are located not just in the full height segments, but above and below our openings as well. And this can be done around a single opening or a longer wall section as shown here. And then the final option is the perforated method, and this is based on testing that originated in Japan. It's been tested, more testing's been provided in the United States, different universities, and we have had this in the code for quite some time. What this does is it looks at the wall, again, with the sheathing for the full wall length, and then you're going to calculate a reduction based on what the percentage of your full height sheathing is, and then what is the maximum size of your opening. So as you would imagine, the larger the openings, the larger the penalty would be on the design, and the less the full height sheathing provided, the larger the penalty. So we'll look at that adjustment factor table in a minute. For our segmented design again, we see that in addition to the sheathing for our full height segments, you'll design and specify your hold downs to resist the overturning, and then the anchorage for the sliding at the bottom of the wall. One of the main advantages for force transfer around openings, as I mentioned earlier, is the height to width ratio. So again, now you're looking at the height as being the height of the opening it's adjacent to. So this gives you a lot more flexibility in how you can apply it to narrower wall segments. The challenge is that this is not based on testing, and so the analysis is per rational analysis, and that can depend or vary based on the engineer and as well as the plan checker providing the review as to whether or not you agree with the rational analysis that was used. So APA has done some additional research into looking at the common analysis methods that are used based on our survey, and then testing these walls and showing which test method, or which rather analysis method closest matched the measured strap forces. And finally, our perforated shear wall option is shown here. And again, you're back to your full height for your height to width ratio. So this is a limitation when using perforated shear wall as opposed to force transfer on opening, because you have to meet that entire wall height as opposed to just the segment next to your opening. And there are pros and cons to both methods. The advantage here is you notice that the strapping has been eliminated, so there's not a requirement for strapping on the exterior of the wall or blocking on the inside of the wall. Hold downs are provided only at either beginning and the end, and that actually is the same when we back up for force transfer on opening. So this is one benefit of both FTAO and the perforated method, is that you are eliminating the hold downs that would otherwise be required on the interior of the wall. Now when you do your FTAO design, you might find that you do need to have some uplift resistance in the form of a hold down in these locations, but that's not a requirement necessarily. So the anchorage as shown for the overturning, but then for the perforated, another aspect is that you have to provide a detailing for this uplift and shear underneath the wall segments that takes that penalty that I mentioned before, looking at the opening, largest openings in the wall, and the percentage of full height sheathing applied to this attachment. So let's look a little closer at the perforated method. It's in the SPDWS section 4.3.5.3 that defines how the method is applied and the limitations that you have to meet. So for your perforated shear wall, you're looking at the entire wall line, sheathing above and below the openings. You do have to show that you have a wall segment at the beginning and the end that meets your height to width ratios, as shown here. Openings are allowed beyond the ends, but they would not be included in the width of the perforated shear wall. So here is an example where you would have a doorway or perhaps a window in the corner. This cannot be considered the beginning of your perforated shear wall as a result. And so a drag would have to be designed to make sure that we are getting the load into the beginning of your perforated shear wall. The aspect ratio limitations still apply as discussed, and so for wind that would be 2 to 1, and seismic that would be, for wind that would be 3.5 to 1, and for seismic that would be 2 to 1, or you can do the 3.5 to 1 with the penalty. And then the nominal unit shear capacity is limited to 870 pounds per lineal foot for allowable stress design. This is a benefit from additional testing that has occurred, which allowed this method to be applied to larger shear required walls. So in the past, the limitation was actually much lower, and so if you like this method and would like to utilize it more, be aware that you can use it for up to 870 pounds per lineal foot for ASD. For out-of-plane offsets, anytime you have an out-of-plane offset, that's considered a unique perforated shear wall. And then collectors for the shear wall should be provided for the full length as typically used with our top plates. You need to have a uniform top and bottom of the wall as shown on the left-hand side. The right-hand side would not qualify. However, if it did have the top plate running along here, and then there was a shear wall mechanism or shear transfer mechanism provided by the engineer of record, then I believe you could use this method in this case. Your maximum perforated wall height is limited to 20 feet. And as mentioned before, you're going to calculate your percentage of full height sheathing and also look at the maximum opening size to go into your table for your adjustment factor. So in this case, perhaps A1, A2, A3, and 4 all meet your height to width ratio requirements. But if A2 happened to be too skinny to meet your 3.5 to 1 ratio, then you would just add up A1, A3, and A4, divide that by the total length of the wall, and use that lesser percentage when you go into the table. Because as you'll recall, you have to have a panel that meets the height to width ratio at the beginning and the end, but it does not dictate that all panels meet that. They just wouldn't be able to contribute when you go into your adjustment table. They will still be sheathed and nailed, though, like the rest of the wall. The maximum opening height is the second thing to consider. So walls that have doorways are going to have a larger penalty than walls with small windows. If you think back to the photo that I showed earlier, where perforated might be most likely used was the wall with the very small window openings. So as we look at the table, we'll see that small openings have much less impact on your design. So your shear capacity is going to be equal to your nominal unit shear times the sum of the full height length times that adjustment C sub O. Here's the table that is found in the SPIDWIS, and that, again, the two variables you need to identify would be your percentage of your full height sheathing, as shown on the left-hand column here, and then your maximum opening height, as shown on the right row at the top. And then this is our adjustment factor that you're going to take depending on those two variables. And you can interpolate between them if you find that you've got 45% of full height sheathing, for example. And just comparing, as I mentioned, very small openings, your adjustment would be 1.0. What happens when you multiply or divide by 1? You're not actually changing those loads. So because having the sheathing above and below all of your windows and doorways, you are providing a stronger wall to begin with that is acknowledged, and you get the benefit of eliminating the strapping, the blocking, and those additional hold downs that would otherwise be required. That being said, as we track along one of these rows, you'll notice that as the opening size gets larger, then your penalty becomes larger. And the same is true if we are looking at an opening height here, and as we see the more the full height sheathing provided, that's going to be less of a penalty. Or speaking alternatively, if you have less full height sheathing, it would be a larger penalty. So putting it all together, you'll note the equation at the bottom where you're going to add up all of your full height segments that meet your height to width ratio. You would apply that penalty of 2 times the width over the height if it's a seismic control design that does not meet the 2-to-1 aspect ratio, and multiply it times your C sub O. As mentioned earlier, you do have to apply that same reduction to your uplift anchorage as shown here, so that T at the bottom of the wall is basically the shear times the height divided by the sum of those lengths and divided by that penalty. This is identified in the SPIDWIS. The same is required for your in-plane shear anchorage for the perforated shear wall. And the reason why they have these requirements for this detailing at the bottom of the wall, because it is based on testing, they wanted to be sure that the failure occurred in the attachment to the base and not at the attachment of the sheathing to the studs. So to summarize again, depending on your attachment, your geometry, you might have less of a penalty that's applied. You do have to show, though, that you're meeting those requirements for the nailing as well as the detailing at the bottom of the wall. The hold downs would also have that same penalty applied to it as well, which we'll see in an example. We'll come back to our shear wall examples. I do want to touch on some connection issues next. So first, the fastener specification. The question came up during the break about what happens if I specify a 10-penny common nail and they use a 10D box nail, for example. So again, it's going to be a different dimension. So common nail really isn't the common fastener today. APA continues to use common nails in our research just for ease of testing, and we recognize the fact that many different types of fastener sizes and dimensions are being used with nail guns at the job site today. What we recommend is that you specify not only the 10-penny common, for example, but a complete specification which includes the nail diameter as well as the length, so that if they do use something else, it's much easier to show equivalence. And as I mentioned, Isanta has a code report that you can find on their website or on the ICCES website to provide you with those substitution tables, or you can do a direct design that way if you know what they're going to use at the job. Overdriven fasteners, 3x requirements, steel plate anchorage, these need to be addressed as well. I believe I have some slides on overdriven fasteners. If not, I will speak to that at the appropriate time. So looking at our 3x requirements, these are referenced from the footnotes to the tables for your shear wall and diaphragm. When do we need to have 3x requirements? Often it's when you have really high shear requirements, which is going to then require tight nailing, large fasteners, therefore the larger members to prevent those members from splitting. So 10-penny common nails at 3 inches on center, or 8-penny common nails at 2 inches on center, or double-sided shear panels that are not offset front and back. Those are all cases that would require 3x's to support them. And as I said, it is covered in the footnotes to the table. So here we see again when the allowable shear is greater than 350, if you have double-sided walls without the panels offset, the nails are spaced at 2 inches on center, or 10-penny nails at 3 inches on center. What about the option of using, instead of a 3x, if you want to use two 2x framing members? And so that is okay, as shown here in the diagram. You see that you need to attach them. And this attachment should be equivalent to the nailing at your edges. So it's going to be a lot of nails and unlikely to be worth the effort of using two 2x framing members as opposed to a single 3x framing member. The issue often is if this was more of a design fix, they would have started with this diagram, and just by adding one on one side, you're not going to get the same impact as what you get here, because basically what this is doing is it's separating the nails on different framing members. You would want to make sure again that you're able to provide that separation of staggering the nails and not splitting the framing. Square washers are required at the sill plate when the allowable shear is greater than 400 pounds per lineal foot for wind or seismic, and there is an exception to eliminate the need for them if interested. If your shear is less than 490 for wind, height to width ratio is less than or equal to 2 to 1, and the overturning is designed per 4.3.5.1 with a standard cut washer. Yet, again, like the topic of toenails versus 3D connections, we feel that the larger washer is cheap insurance and is really shown through testing and performance that it's a much better detail to resist this cross-grain bending that is occurring in this attachment, and that this larger washer goes a long way to prevent that failure from occurring. Getting into our shear wall, so again, I did not touch on overdriven fasteners. So we do have our white paper. I believe that was TT012, and that gives you some design guidance. If you have a situation where your fastening has been overdriven, what is your design solution? So we have some prescriptive options that are detailed in the white paper, and basically if you have less than 20% overdriven by less than 1/8 of an inch, you're able to prescriptively add one additional fastener for every 2 that are overdriven, unless you're already at 2-inch on center nailing, for example, where we know if we added additional nails, we could cause splitting to occur. So if that is the case, at that point you would want to take a second look at your design. Perhaps you had a little extra room in your design where if you acknowledge that it has been overdriven slightly, you would assume a thinner panel for that nailing that was provided. Perhaps that will meet your design needs. If that does not work for you as well, then staples might be a solution. If you provide staples, you can't provide just enough staples. You would need to staple the panel as though the nails were not there, and that shouldn't cause splitting to occur, but would provide the shear capacity that you need. One other item covered in that white paper is if the nails weren't actually overdriven, but if the panels were exposed to enough moisture that the panel actually had swollen around the nails, then there's no reduction required, because that capacity is based on the size of the wood members, and if you cut a section through that, you would see that the nail was still holding the thickness of the panel that you had assumed in your design. As long as the panels are allowed to dry before being enclosed in the wall envelope, there shouldn't be a reduction in the strength, because the panels will regain their strength when dry. So again, it would just be an aesthetic issue, but it would not be a shear reduction. Moving into our shear wall design examples. For a 26-foot long wall that's 8 feet in height with a doorway and 2 windows, a shear force at the top of the wall of 3,750 pounds. If we do this per segmented design and don't account for any sheathing above or below the windows, regardless if it's there or not, we would need to look at our height to width ratios. So again, we see that the 4-foot segments would meet that 2-to-1 aspect ratio. The 3.5 would meet the 3.5-to-1, yet if this is a seismic control design, you would need to apply the penalty of 2 times the actual width over the height. Our unit shear, you would take the shear at the top of the wall divided by the length of your full height segment. So added up, you had 15 feet of shear panels, so it would be 250 pounds per lineal foot. And then 2 solutions are shown here for the different lengths of the wall, yet you'll notice that you have the same thickness of sheathing, 15/32 rated sheathing, 8 penny nails at 4 inches on center for the 3.5-foot long walls, at 6 inches on center for the 4-foot long walls. Do you think it's a good idea to have 2 different nailing patterns in a single wall line? I do not either, so I would recommend that you would use the 8 penny nails at 4 inches on center for the entire wall line. The next item down is our hold down forces. Again, that's 250 pounds times the height of the wall, so 2,000 pounds. You would have 8 of those for each of your full height segments, 2 on each of your full height segments. And for simplicity's sake, we're not taking into account any dead loads on this example. So in the end, you have 15 32nd rated sheathing, 8 penny at 4 inches on center, and 8 2,000-pound hold downs provided. If we look at the perforated shear wall, instead, same dimensions and opening sizes. We still need to look at the height to width ratio, so the penalty is going to be applied for a seismic controlled design, same shear at the top of the wall. We have to calculate your percentage of full height sheathing and look at the largest opening size. So 15 feet of full height sheathing divided by the total length of the wall, you find 57%. The maximum opening height is 6 feet 8 inches for your doorway. Now going into the table, as mentioned earlier, you can interpolate between 50 and 60% to precisely find your value for 57%. And then for this opening size, you would interpolate to take 0.61 as your shear capacity adjustment factor, CSIBO. That value is now going to be applied to your shear resistance. So this 490 is based on 15 32nd rated sheathing, 8 penny nails at 3 inches on center. Same grade of sheathing, same thickness, same nail size, but tighter nailing. We also have to apply that adjustment to our hold downs. So rather than 2,000-pound hold downs, you have 30 to 80-pound hold downs. Larger hold down capacity required, yet 2 of them as opposed to 8 total. And then the in-plane shear anchorage and uplift anchorage. And how this is detailed is up to your engineering creativity to provide that connection. The deflection would also need to be designed with that adjustment factor into account, the CSIBO. So to look at a summary of what these walls look like using the different approaches for segmented design and perforated, and even force transfer on openings, which I did not go into detail for that method, you'll note that they all have the same sheathing thickness and nail size, but the nail spacing is going to decrease from 4 inches on center to 3 inches on center for the perforated method. The hold down requirement, it goes from 8 hold downs for segmented to 2 hold downs for FTAO or perforated. The perforated, on the flip side, does require detailing underneath these full height segments, whereas the force transfer would require strapping around your windows and blocking on the inside of the walls. You'll note with the force transfer, when you calculate those hold downs, it's actually much less, 1550 pounds, because you take the entire length of the wall as your resisting lever arm in that calculation, and so it's a much smaller force that you design for. The other thing to consider is, what if we started our perforated wall here, just like the force transfer on opening wall? What advantage would that present us with? Yes, we would have smaller window openings. So with the smaller windows, now your penalty would be much less, that you take the CSIBO value and you would have a more efficient design provided. On the topic of code updates, I did want to briefly mention the option for prescriptive lateral design for the wall bracing section of the IRC. And what this says, if you're not familiar with the residential code, and the residential code, as the name implies, is to be used for residential buildings, single family, 1 and 2 family structures primarily, and it gives you the option in R602.10 that says where a building or portion thereof does not comply with one or more of the bracing requirements in this section, those portions shall be designed and constructed in accordance with section R301.1. What do you suppose R301.1 says? It is a reference to using the IBC. So this allows you as an engineer to use both of these codes to provide your design. I have discovered that there is engineers that do just that. They use the IRC and when they're doing their residential design, and where it doesn't meet those prescriptive requirements, they'll provide it per the IBC. And so what's the difference between the two? Well, the residential code is more like a recipe, and it says you have to have these certain ingredients or the limitations as shown here of being a residential building, 3 stories max, wind under 110 miles per hour, size and design category A through D2. There are other limitations, of course. But if you meet those ingredients, then you follow the recipe and provide the wall bracing. You're going to have braced wall lines as opposed to shear wall lines, and similar to shear walls, you'll have braced wall panels that will be spaced within 10 feet of the ends and 20 feet between their edges. Furthermore, checking against a shear, a earthquake and wind table to show that you have enough per that wall line to meet the prescriptive requirements. And like I said, with our engineered options, you are really calculating those forces precisely, providing your design as we've gone through in great detail with your diaphragm to transferring the forces to the shear walls. Then often the big difference between the two methods is that the braced wall panels will require fewer hold downs than our shear wall design will. So for more information on this topic, APA does give seminars on this topic of up to 8 hours in length. We also have our guide to the 2012 IRC for wood wall bracing provisions that's produced with ICC. It's available on their website for purchase. We have many publications that are available for free download, as shown on the right-hand side. Unfortunately, they're based on the 2006 residential code in general, so if your jurisdiction is still on an older code, that's applicable, but there have been enough changes in the 2012 that I would recommend going to this document or the code directly for your assistance. The last item I wanted to share with you before we wrap this up with our final Q&A is to look at the FTAO research project that APA recently conducted. This was a joint research project between APA and the University of British Columbia and the USDA Forest Products Lab. The UBC provided some finite element analysis modeling, and the Forest Products Lab were involved in the review, the report writing, and the documentation. APA did the testing at our research facility. The goal of the study were multiple things. We wanted to look at the variation of walls with code allowable openings. So the opening sizes varied from smaller to larger. We also had height to width ratios that were 2:1 versus 3.5:1. We furthermore looked at different level of detailing, beginning with segmented walls where there was no sheathing above or below the openings, to simply adding sheathing, eliminating those hold downs that would otherwise be required, then providing blocking on the inside of the wall and strapping on the outside of the wall to get to a full FTAO detailed wall. We looked at the strap forces that were measured again. So as noted earlier, with FTAO, there's not one black and white rational analysis method out there to be used. And so we looked at the common ways that engineers often analyzed FTAO and then compared it to what was measured in our testing to see which one closest, which calculation matched the measured forces most closely. From our results, we wanted to identify which analysis method would be recommended, and also the level of detailing, what is preferable. Even better, is there something new and that can come out of this, a new tool or methodology for engineers to utilize in designing our shear walls with openings. And that is the current state of affairs. We have very interesting buildings with a large opening, lots of design features, so we want to be able to still provide a safe structure and an interesting one at the same time. So some photos just demonstrating where we often see force transfer around openings being used. And again, as I mentioned earlier, the height to width ratio is often driving the need for them. We see the strapping provided around these windows on this residential structure, as well as around the windows in this case, and then a much larger podium structure, which really amplifies the aspect of having a lot of bump outs and narrow segments surrounding our openings. So the need for some alternative solutions. In surveying structural engineers, we identified the following methods as the 3 common rational analysis methods: the drag strut, cantilever beam, and the Diekman method, which is very similar to the Breyer, Cobein, Thompson, or the SEOC, Structural Engineers Association of California Blue Book method. It has a lot of different authors that you could attribute this analysis method to, and we'll look at the resources where you can get more information on them. Quickly just comparing the techniques, we see with drag strut analogy, as the name implies, you're dragging the load above and below their openings, and it's based primarily on the geometry of the wall. For your cantilever beam, you're going to break this into individual segments to then do your moment analysis or find your bending moment to calculate the forces for your straps top and bottom. And so again, thinking about geometry, this can have a large impact on what you're going to calculate, because where do we typically have more sheathing provided, above or below our window? Below. So because of that, having more sheathing below, you're going to calculate a smaller force here than you will up here. And then the question is that actually what's being transferred to the straps? And then finally, the last method, as we'll call the Diekman method here, you're breaking this down into a series of force body diagrams and resolving the forces based on the principles of mechanics. This photo shows a typical test wall, and you'll note that we use oriented strand board for our sheathing and strapping on the outsides of the wall when we did the full FTAO wall. If you look closely, you'll notice those are actually hold downs that were mounted on the outside of the wall, and no, we do not think that people are putting hold downs. We understand they're flat straps. This was done for ease of research and mounting the monitors on them. We further tested with flat straps to show the same answers were recorded, or forces were measured, and then Simpson Strong Tie also did a test with flat straps and showed the same results. So we wanted to examine the forces in the straps above and below the opening, look at the failure modes, and then test walls that could be modeled. I mentioned that OSB was used, and you may wonder why we used OSB as opposed to plywood. We also used Struck 1 15/32 performance category. So we wanted to use the thickest sheathing with the tightest nailing, 10-penny common nails at 2 inches on center, so that whatever results we find from this research can be applied to the broadest application in shear wall design. As I mentioned earlier, with the perforated method, there used to be a limitation to the shear capacity because they used a lesser panel thickness and nailing pattern to be originally. And so they had to do further testing to be able to extrapolate that. We wanted to be able to maximize our research for the outcome in the end. So that's why the thicker, higher grade sheathing with the tighter nailing was used. And we used OSB as opposed to plywood because there are some people who prefer plywood, feel that plywood has better properties. So we felt by using OSB that the plywood preference people would be okay with the results and say, okay, if it works for OSB, it works for plywood. Whereas if we had done the reverse, that might not have the same implication. Walls were all 12 feet long and 8 feet tall. There were 12 different wall configurations, as I mentioned, that began with a different level of detailing of segmented all the way through FTAO, and they were tested using the cyclic loading protocol following ASTM E2126 Method C Curie Basic Loading Protocol. So we see with our test plan just 4 different options. There were 12. Notice this was segmented, no sheathing. Second, we added the sheathing. Third, we added the blocking. Fourth, we added the strapping. That was done for various height to width ratios as well as opening sizes. Ultimately, we found that the more material provided, the more level of detailing, the better the walls performed. The strength of the walls and the stiffness. And the larger the openings, the lower the stiffness, as you would imagine. And the strapping requirements were greater as well, the larger the opening. Talking about the strap forces specifically, and all this data is available on our website that you can peruse at your leisure. We did compare the common analysis methods, as mentioned earlier, shown at the top of the drag strut, cantilever beam, Diekman, or the SIOC method, in comparison to the different wall configurations and the measured strap forces. So the yellow identifies unconservative results. We found that what that was predicted was less than what was measured. Cantilever beam was very conservative, and then the Diekman and SIOC method were most accurate. So for our conclusions, as mentioned earlier, the greater the level of detailing, adding sheathing alone, the wall performs better. Adding the blocking and the strapping, again, the performance increases, was better for the overall performance. And then comparing the analysis methods, the drag strut technique was consistently unconservative. So if you have used that method in the past, consider not using it again in the future. The cantilever beam method was consistently ultra-conservative, whereas the SIOC and Diekman method were most accurate. We're still working on outcomes for better methods moving forward. If you have ideas, we would love to hear them. Please let us know. The report is available on our website at apawood.org. You can search for it, putting in force transfer or M410. And that concludes our agenda for today, load path continuity through the building code updates and our shear wall design alternatives. I would just again say thank you for sharing your time with me, and please don't hesitate to contact myself or another EWS that's closer to you perhaps in your region, and we look forward to assisting you.